In this video, I introduce Bayesian inverse reinforcement learning. Inverse reinforcement learning is used to find the reward function in Markov decision process, given the system dynamics and the expert demonstrations. Suppose the expert at state SA follows his own policy and generates this trajectory. We can observe the expert at state S1 takes action A1 and moves from S1 to S2. However, we cannot observe the reward function from the expert behavior. So our agent needs to use inverse reinforcement learning from this trajectory to find the reward function. And then use this reward function in the reinforcement learning to find the optimal policy. Now, Bayesian inverse reinforcement learning formulates inverse learning problem as a Bayesian inference problem. And then the maximum posterior is used to train the model and find the reward function from the posterior distribution. To do so, Bayesian inverse reinforcement learning uses the expert trajectory as evidence in the Bayesian inference, and use the cumulative reward R as the hypothesis in a Bayesian inference. Once we get this Bayesian inference model, and that means we give a trajectory. And then we use maximum posterior to train and estimate this posterior distribution. That means given a trajectory, we can find the reward function from the Bayesian inference model. To do so, we need to define this likelihood and the prior of the reward function. Now let's see how can we define the likelihood. Suppose our agent generates a trajectory using suboptimal policy, not an optimal policy. So that's where we cause the degeneracy issue. That means the trajectory O, policy pi, and reward R are not a one-to-one relationship. So we need to use the maximum entropy principle, deals with this ambiguity by finding the trajectory O with the maximum entropy. So to find the reward from posterior distribution B, we need to define the likelihood and prior P distribution. Intuitively, we can see this likelihood, for a given reward R, we can calculate the probability of this trajectory to be the true trajectory. Because, the higher reward will make the trajectory have a higher probability to be a true trajectory. That means we define this likelihood using this exponential, because this reward may be negative, but we just use this exponential to make sure this likelihood always positive. And because this each cumulative reward is defined over the trajectory, so we need to normalize all of them together, to the one. That means we use the softmax function here. This is a normalization factor. And then let's see where is the degeneracy problem. For example, given this reward R, and then we use this reward R in the reinforcement learning to find the optimal policy. However, here the policy is not optimal policy, it's a sub-optimal policy. So that means for each real-world R, we will have multiple policies. And each policy will generate their own trajectory. Then that's, we have a problem because, one real-world function will corresponding to multi policies and multi trajectories. So then we use this likelihood in Bayesian inference, and also bring this the generation issue into this Bayesian inference. To overcome this problem, we define the loss function as entropy loss function. That means we define this loss function as a log p. And use this way, we find the p with the maximum entropy. And then we find the real-world function we need. And then let's see how can we define the prior distribution. If we don't have any information about the prior, then now we can use the uniform distribution. That means we select this prior equal to 1. Otherwise, if the real-world function is a negative real-world, and then now we can use the Gaussian prior or we use the Laplacian prior. Because in these two priors, even the real-world is negative, we still can get the prior distribution is positive. And if the real-world distribution is a sparse real-world distribution, that means we only assign a real-world or large real-world to the goal state, and then now we use the beta distribution as the prior distribution. And just like this is the shape of the beta distribution. For more details, please check with this reference. Thank you. Bye.